Have you ever asked yourself the question, what is a VLAN versus an interface VLAN? If that question at least once has crossed your mind, this video is for you. We're going to take the router on a stick that we did in our previous video, and we're going to collapse the network down to have the integrated routing functionality be done by the switch itself. No external router, no external interface for the router. We'll do it all with something called a switched virtual interface. Let's jump in. So let's take a look at the migration towards nothing. Eventually we'll have one box that can do it all, and there are devices that do all that functionality, and the question I guess could be, do you really want to put all that functionality in one box? The answer is, if you replicate everything and you have fault tolerance, why not? So here in this example, we have migrated to one router with one physical interface trunking from the previous video, and we're doing routing based on the logical sub-interfaces. Well, if these are just logical sub-interfaces for the purpose of routing, we can totally remove this router if our switches are multi-layer switches. What is a multi-layer switch? I'm glad you asked. A layer 2 switch makes forwarding decisions based on MAC addresses. That's what we know and love switches as. However, what do you call a device that makes forwarding decisions at layer 3? Well, normally we'd call it a router. But if we trained a switch to make forwarding decisions at layer 3, guess what? That switch, if it can forward it based on layer 2 MAC addresses and make forwarding decisions based on layer 3 IP addresses, it's now graduated to the class called a multi-layer switch. So if we do get rid of the router, so it's completely gone, we turn off this port on the switch and we power off R5, what about our clients? Let's think about this from the PC's perspective. It's got an IP address of 10.0.0.10. It believes that its default gateway is 10.0.0.2. And you know what we should do? We should probably provide a default gateway for that client. But instead of having the router do it, we're going to go ahead and have the switch do it if it's a multi-layer switch. There's a couple processes here that have to happen. One is we need to enable on the switch IP routing. By default, on most switches that are capable of doing layer 3 forwarding, the command IP space routing is turned off. So we'll need to turn that on. And then secondly, we need to create out of thin air a layer 3 address that this guy here can use as his default gateway, the 10.0.0.2 address. So we're going to do it very much like we did on this router, except we're going to do it on the switch itself. Instead of saying interface FA00.2 or 00.3, we're just going to go into global configuration mode and say interface VLAN 2. Let's stop the bus right there for a moment. When we type in interface VLAN 2, that is not creating the VLAN. The VLAN 2 already exists. We assign this port to VLAN 2. The trunks are allowing VLAN 2. VLAN 2, the broadcast domain, already exists. What this command right here is doing, it's creating a layer 3 logical interface, like a router interface, that lives in VLAN 2. So we are creating an interface VLAN 2 that can support users that are currently in VLAN 2. The second thing we're going to do is need to give it an IP address. So we'd use the command IP space address and give it the IP address we want to. In this case, 10.0.0.2. Now take a look at that IP address. Why that IP address? It's because the customers in VLAN 2 are looking to use 10.0.0.2 as a default gateway. So we're going to assign the IP address that customers need to the virtual interface. They call it a switched virtual interface, interface VLAN 2, and give it the IP address. We're going to do the same thing for our good old customers here in VLAN 3. We're going to create a logical virtual interface called interface VLAN 3 to support our customers in VLAN 3 and give it an IP address that the customers in VLAN 3 are supposed to use as their default gateway. So these are real layer 3 IP addresses. But if you got out your microscope and said, let me see exactly where those interfaces are, you will never find them because they're not physical. Just like you wouldn't find these sub-interfaces from a physical perspective, you won't find these switched virtual interfaces either. And you know what? A switched virtual interface is not that uncommon. Think about it. Do we ever have to manage our switches? The answer is, yeah, we might need to telnet or SSH to them. We have been using switched virtual interfaces forever because it's a switched virtual interface we create, interface VLAN 1, and assign it an IP address. that allows us to remotely telnet or SSH or open up a browser access to a switch. So all we're doing with multi-layer switching is we're saying we're not just going to use an IP address for management of the switch. We're going to use at least 2 interfaces and enable IP routing, so the switch that we configure these on can literally be the router for our 2 VLANs. All right, so it's now time to configure this. It's a lot of fun and it's super easy. The very first thing I want to do is point out that we have turned off router 5. It used to be the router on the stick up here. We've physically turned it off, so we're not going to have a conflict of IP addresses. You can only have the same IP address being used one time in each subnet. So switch 1 is going to use the IP addresses of 10.0.0.2 and 30.0.0.3. For the VLAN 2 interface, it's going to use 10.0.0.2. Why? Because that's what the clients on that subnetwork have been trained, either through static configuration or DHCP, to use as a default gateway. And we'll do the same thing for the VLAN 3 interface. We'll use 30.0.0.3 because the clients are expecting to use that as a default gateway. We also need to make sure we turn on IP routing, which we'll do. Otherwise, even though a switch might be capable of layer 3 routing, it doesn't like to do it most of the time by default. So we'll use the command IP routing. So let's start right there. We'll go into configuration mode, and in configuration mode, we'll simply say IP space routing. Poof, no beautiful console message or anything else, but now it's able to route packets. Next, we'll create our logical layer 3 interfaces. We'll create interface VLAN 2 and interface VLAN 3. And as a reminder, the VLANs 2 and 3 already exist. We're just creating the interfaces, the logical interfaces that the switch is going to manage that we can put IP addresses on. All right, so now that that part's done, let's go ahead and create interface VLAN 2 first. And the syntax is really, really simple. You just go from global config and say interface VLAN 2, enter. Now, if the VLAN 2 broadcast domain doesn't exist, this interface is worthless. But assuming it exists, we create VLAN 2, assign it the IP address, and we're good to go. And just like any other interface, it's up and active. Now we'll create a second logical interface. We'll create this one right here for the benefit of customers in VLAN 3. So we go into interface configuration mode, global config, and then say interface VLAN 3, which puts us into interface configuration mode, and then give it an IP address. That is it. That's all we need to do. No routers required because in this case, switch 1 with these 2 logical interfaces is acting like a router. Now, could we have done these commands over on switch 2 on the left or switch 3 on the right? Yes, it really doesn't matter. I picked a middle point, but these logical interfaces could be anywhere where that VLAN exists. And because the red VLAN, VLAN 2, is allowed across all the trunks, we literally could have had these commands on any of the 3 switches. Now, let's go ahead and test this. For our test, we're going to put a protocol analyzer on one of these links, and that brings us to an important question. We have these trunk links going between the switch on the left, the middle switch, and the switch on the right. And these trunk links, if we have 2 parallel paths between 2 switches, what happens? Well, if spanning tree isn't running, we have a loop. But spanning tree is running here. And so spanning tree is only using one of these links. So I'm going to monitor on both of them, and then we'll go ahead and simply take a look at the protocol analysis on the trunk that was active. In the next video, I'll show you how we can take these 2 trunk links where only one of them is active because of spanning tree and bundle them together into an ether channel. So we're not wasting any bandwidth. But for now, we just realize that only one of these interfaces is going to be active for forwarding traffic because of spanning tree. So what do we expect to happen? In fact, let me just clear out anything that might be in memory here. On the PC, I'm going to go to configuration mode and interface FA 0/0. I'm going to shut it down. This PC is being played today by an iOS router. So by shutting it down, that forces any kind of resolution for layer 3 to layer 2 mappings. They're going to be completely gone. And I'll bring it back up as well. So we'll do a no shut, and that will come up. Now, we are connected to a switch port here. So I would want to give it, if I haven't configured rapid spanning tree or port fast, we'd want to give it a few seconds to make sure that the PC has the ability to forward traffic on the network. Let's do a show ARP real quick and verify that there's nothing in the ARP cache. Now this MAC address right here, I've hard-coded on this PC, so it's 10101010. It's really easy to recognize. And here's what we expect to have happen. When this PC tries a ping of 30.0.0.10, the very first thing it says to itself is, and you know the answer to this now, it says, is this network 30.0.0, is that local or remote? And it's assuming it's a 30.0.0, it's a 24-bit network because it has a 24-bit mask. That's what PCs do. They assume everybody has the same mask they do, and then they ask the question, is it local or is it remote? Well, in this case, 10.0.0 is different than 30.0.0. It's like being on two different streets, and as a result, the PC knows that it needs to go to its default gateway for help. This device is configured with the default gateway of 10.0.0.2. So it looks at its ARP cache and says, oh, I don't know how to get to the layer 2 address of my default gateway, and I need it because that's how we forward frames at layer 2 is based on the destination MAC address. So it's going to do an ARP request. This ARP request is going to go out, it's going to go into the switch as a broadcast. It's going to go over one of these trunk links. This switch is going to get it. This switch is going to forward it across its trunk links as well, so that everybody who is possibly inside of VLAN 2 will get this broadcast. Now, the switch on the right doesn't have any access ports in VLAN 2, so it won't forward them to any access ports here, but the broadcast would be received on the trunk link between the middle switch and the right switch. Okay, so the broadcast goes everywhere. This switch in the middle, once it has the IP address, which we just gave it of 10.0.0.2, is going to see that. It's going to say, oh, you're looking for my MAC address. And it will respond with the MAC address that it has decided to use for this logical interface. That response is going to go back over the trunk as a unicast back towards the source MAC address of this PC. And the PC will get it, and all of a sudden, the PC will have a new ARP entry. It will know that 10.0.0.2 is reachable by whatever MAC address the switch has assigned to that virtual interface. Great. Then what happens? Well, then the PC sends a packet. If we do this ping right here, the ping packet, the request, will go from 10.0.0.10, its IP address, to 30.0.0.10. So at layer 3, that's the source and destination. But it's going to be forwarded to this logical interface on the switch, and the switch is going to say, oh, I'm a router now. I have IP routing enabled. I need to forward this packet to the 30 network. I'm directly connected. I need to figure out what the layer 2 address is of this server. Does this story sound familiar? This is identical, my friends, to the story we had with router on a stick. It's also very similar to using multiple physical interfaces for routing. We have to figure out what the next layer 2 address is as we forward packets along the way, or in this case, frames along the way. So this switch is going to say to itself, I don't know what the layer 2 address is of 30.0.0.3. And as a result, what is it going to do? It's going to generate a broadcast, specifically an ARP request. Please respond with your layer 2 address. Now that broadcast, check this out, because we did it right here, that broadcast where this switch is asking for the MAC address of 30.0.0.10, that broadcast, because it is associated with VLAN 3, it's going to go down this trunk. It's also going to go down this trunk because these trunks are allowing all VLAN traffic. Now this switch on the left gets that broadcast and says, I've got no access ports assigned to VLAN 3. So I received it with a tag. It says this is for VLAN 3. This switch says I don't need it, and it wouldn't actually send it to anybody on this switch because it came in on the trunk and there's no other access ports. However, we can mitigate that wasted bandwidth of having a broadcast come down here if we use a technique called VTP pruning. But just to be clear on what we expect to happen, that is the expected behavior. So if we track or sniff the wire on these two interfaces, whichever one happens to be active from a spanning tree perspective, we are going to see the ARP request of this client looking for the layer 2 address of 10.0.0.2, and we're also going to see the reply come back, and we're also going to see an ARP request for VLAN 3 looking for 300010 on this segment, but we won't see a reply. Why is that? The broadcast went out left, the broadcast went out right, and the response came from the server back over to the VLAN 3 logical interface. So the unicast reply won't be seen over here. And then we should see the remainder of the successful echo requests and echo replies going across the network. That's the theory anyway. So let's go ahead and do a ping. Give me a moment. Let me put the protocol analyzer on go mode so it's listening to both of these two interfaces. And now that that's done, let's go ahead and do our ping. We also should lose 2 of our ICMP echo requests. Why is that? One, we lost on the initial ARP for looking for 10002, and one as the VLAN 3 interface was looking for the MAC address for 300010. And there you have it. And if we do a ping again, we should have 100% because all the ARP resolution is done. And if we do a trace, the trace route should show that I need to put in an IP address 30.0.0.10 because that's where we're going. We'll use our default source address and let it go. All right, so the first hop was our default gateway of 10.0.0.2, and the final destination was 30.0.0.10. And so when a Cisco router does a trace route, it's actually sending 3 UDP segments with a TTL of 1, which causes the first router to say, hey, I'm killing those packets, here's your responses, and this is how long it took to get those responses. Then we increase the TTL to 2, and we send out the 3 segments again. And that gets past the first router to the final destination, who doesn't have any services, who also sends an ICMP response saying that the destination is not reachable because I'm not running any services on this port. And those ports are done dynamically behind the scenes. We don't have to manually put them in. Okay, let's take a look at the protocol analyzer and verify what we thought would happen with the ARP requests and the actual ping packets as they went over this trunk. Spanning tree is a chatty little protocol, isn't it? Most of the stuff we captured is related to spanning tree, where every 2 seconds for every instance of VLANs we have, by default, we have little BPDUs going out. So let's scroll down to our first relevant packet, and that is right here. So the moment we typed in ping 300010 from this PC, it said, ooh, it's remote, it's not local. I need to forward this to my default gateway, which is 10.0.0.2. I don't have his layer 2 address. I need to find it, and that's what this ARP request is all about. You'll notice because we captured it, by the way, it was FA1/11 that was active, and FA1/12 is the one that is currently blocked from the spanning tree perspective. This middle switch happens to be the root switch. So all the action got caught on this top link. So if we take a look at the Ethernet frame, it says, okay, this Ethernet frame is sourced from the MAC address of the PC, which I hard-coded. The destination is a broadcast at layer 2, and the next protocol up is 802.1q. So that's hexadecimal 8100. If we were handing it directly up to IP, it would be hexadecimal 800 as the layer 3 protocol number. So we're handing it up to 802.1q. We'll minimize that. Open this up, and the most important story is this. It says this is a broadcast destined for devices in VLAN 2. Now, how did the switch figure it out? Because the guy who put the tag on is this switch. It's because this switch received the broadcast on an access port that was assigned to VLAN 2. So as he propagates it, he tags it with VLAN 2 before he puts it on the trunk. So this receiving switch who received this knew that broadcast was for VLAN 2 because he read the tag, and then he forwards it out to any other devices that are interested in VLAN 2 traffic, which would include the logical interface VLAN 2 and these trunk ports that lead over to the switch on the right. So it's a .1q frame, and inside that frame we have an ARP request. And this is 10.0.0.10 right here, asking who has the MAC address, or who can tell me what the MAC address is for 10.0.0.2. What is the proper response? Well, the proper response is an ARP reply. And here's the ARP reply. So this ARP reply is sourced from the layer 2 address of this logical interface, which is right here. We can see that. The destination is the unicast MAC address of this PC. It's also tagged as VLAN 2 because that was the interface that sourced it. So before he put this on the wire, he also tagged it as this belongs to VLAN 2. Sent it across. Switches make unicast forwarding decisions based on where they know that MAC address lives. So this switch knows that this MAC address, 1010.10.10, lives off this port. But in addition, instead of just forwarding it, it also checks to make sure that that port is open, if you will, for VLAN 2 traffic. So because it's an access port assigned to VLAN 2, that's a yes. The only other option would be a trunk port, which was allowing VLAN 2 traffic along it. So the response makes it to the PC. He's all happy. He now knows the layer 3 address and the layer 2 address of his default gateway, and one of our pings gets sent off. So if we scroll down here, here's our ping request. So now our ping request makes it to, from this PC, we'll go to the layer 3 information here, from 10.00.10, and the destination is 30.00.10. That's the layer 3 information. But as far as the layer 2 information goes, it's sourced from the MAC address of the PC, and the destination MAC address is our default gateway, 10.0.0.2, that we just learned. Now, unfortunately, this switch, who has two logical interfaces, it gets this packet and says, uh-oh, I need to forward this packet to this layer 3 address. And that is right here, 30.0.0.10. And he looks in his routing table, just like any router would, and says, do I know how to get to 30.0.0 anything? And the answer is yes, in this case, because he's directly connected to the 30.0.0 network. Now let's just do a quick reminder of how a router, whether it's a multi-layer switch or a physical router, how does a router learn about networks, reachability? There's really only 4 options. Number 1, he can be directly connected. In this case, he's directly connected to the destination network of 30.0.0. Secondly, we can use dynamic routing protocols, where you'd have a router that was maybe next a neighboring router who's sharing information with you. So we can dynamically learn about networks and reachability from neighbors. In this case, there's no routing neighbors because we only have one routing device and no routing protocols running. The third option is a static route. We could tell a switch, a multi-layer switch or a router, hey, buddy, to get to some remote network in, Des Moines, Iowa, go ahead and use this IP address as the next hop and statically configure it. And the fourth option would be use a default route. A default route that says, dear Mr. Router, if you don't know how to get to some network, name it like network 2.3.4, go ahead and use this IP address as the next hop. So the 4 options are directly connected networks. Number 2, we could use dynamic routing protocols and learn about reachability from neighbors. Number 3, we could use static routes where we hard code and configure it. Hey, buddy, to get to this remote network, use this next hop or use this exit interface as it might be in a serial point-to-point link. And then fourth, we can use default routes. And default routes could be learned either dynamically or they could also be statically configured. Okay, so that's a little refresher on routing. So this switch says, I know how to get to the 30.0.0 network. I don't, however, know what the layer 2 address is of the final destination. So it does an ARP request. So this is the switched virtual interface that's asking. It says, and look at the trunk. It's sending it out on its VLAN 3 interface. So VLAN 3 interface logically is making a request saying, I'm looking for the person who has the IP address of 30.0.0.10. I would very much love to get your layer 2 information. And if we scroll down a little bit, some spanning tree came in the way. We have no response. And let's talk about that. Oh, gosh. I mentioned this earlier, and now I'm looking for the response. Why aren't we seeing an echo reply or the ARP reply? And here's the reason. This switch here made an ARP request. Because it's a broadcast right here, it went left and it went right. The server listened to that broadcast ARP request and responded unicast. The unicast reply came back to this switch, got forwarded to the switch in the middle based on the layer 2 destination MAC address, and that's why our protocol analyzer over here never saw it. So the ARP reply happened, but it happened over here on this segment. So now this switch knows the layer 2 addresses of everybody it needs to talk to so far on these 2 subnets. And then we have our actual echo requests going through and the replies. So if you take a look at this request, we have the request coming from the PC. They scroll up here a little bit, and that request is being injected into the switch on VLAN 2. You'll notice there that unicast gets forward layer 2 wise to the logical interface on this middle switch. The middle switch routes it between VLAN 2 and VLAN 3 interfaces, the logical layer 3 interfaces, and then it forwards the packet onto the final destination using the layer 2 MAC address of the destination on that local subnet. And the reply comes back, and everything we see here is simply going to be tagged as VLAN 2 because on this segment of our network, it's all VLAN 2 traffic. If we put the protocol analyzer over here, it would be all VLAN 3 tagged traffic. I hope you had a lot of fun. I think everybody deserves really to understand how things are really working, not just logically, but also how the pieces all fit together. In these 3 videos, we started off with physical routers and physical interfaces. We reduced it down in the second video to using a router on a stick with one physical interface on an external router and multiple logical sub-interfaces. In this third video, we've removed an external router altogether by using the built-in functionality of a multi-layer switch and creating logical VLAN interfaces, layer 3 interfaces for the routing process. The last challenge that I'd like to solve in the fourth video, the next one, is what do we do about these pesky trunk links? I mean, really, we have 2 physical interfaces. We're using all the ports. However, only traffic is being moved on one of them because of spanning tree. We'll solve that with the solution called Ether Channel as we bundle FA 1/11 and 1/12 together to make spanning tree believe that we have one huge pipe that is 200 megabits per second as opposed to a single physical interface which has a capacity of 100 megabits per second. Come back and see me for that one, and I appreciate you watching. Have a great rest of the day.